Hello and welcome. In this video, we're going to take another look at Green's theorem. Now, remember that with Green's theorem, we start with a curve that is existing on a plane. It's positively oriented and simple and closed. And Green's theorem relates the line integral of that curve to a double integral of the region enclosed by it. Well, in this video, we're going to be just expanding that in a little different way. Now that we have an idea of curl and divergence of a vector field, we can actually reinterpret Green's theorem in terms of curl. As well as that, we can actually also take a look at how we could maybe use divergence and Green's theorem to combine together and create an interesting result. And these two results are going to expand in the future to further dimensions. So let's start off with reviewing Green's theorem. All right, with Green's theorem, we start off with a positively oriented, piecewise smooth, simple closed plane curve. And D is that region that is enclosed by that curve. And assuming that F is also just a vector field on the xy plane, we'll have its components be P and Q. Now, our Green's theorem says that the line integral of that vector field over the curve is equal to the double integral over the region of partial q with respect to x minus partial p with respect to y. And we can rewrite the line integral in one of these two forms, f dot dr, or component-wise form p dx plus q dy. When we evaluate the line integral, we tend to use the parameterization. And if we're going to be evaluating the double integral, then we turn that into an iterated integral dy dx, dx dy, or possibly r dr d theta. Now, this partial q with respect to x minus partial p with respect to y should look kind of familiar now that we've taken a look at curl. Remember that the curl of f is our vector differential operator cross product with the field, or nabla cross f. If we have a field that is simply on the xy plane though, we will just set its z component equal to 0 and get pi plus qj plus 0k. Then we can compute this curl and get the curl vector 0i plus 0j plus partial q with respect to x minus partial p with respect to y, k. And this is exactly the integrand in our double integral. So another way to express Green's theorem in terms of vector notation is that the line integral f dot dr is equal to the double integral over the region D of curl f dot k dA. And that dot product there, since we are taking the dot product of the vector 0, 0, 1, is simply going to get us the scalar partial q with respect to x minus partial p with respect to y. And so this is precisely the same thing that Green's theorem says, but all written in terms of vectors and not having partial derivatives. When we expand this to a third dimension, we will actually see how this can become generalized to Stokes' theorem. Now, as an interesting result here, remember that this line integral, we can often think about that as being sort of like the work done to move a particle along that path. And here, curl is sort of a measurement of circulation at a single point. And we're adding up all of the curl at every single point in the region. And so it's really thinking that the work done to move an object in this counterclockwise rotation is equal to a sum of all of these little counterclockwise rotations at every single point in the region enclosed by the curve. So it's a very interesting theorem between a boundary kind of integral and an integral of the interior. Now, let's take a look at how divergence can play around with Green's theorem in a sort of different application. Let's start off by setting up the first couple conditions of Green's theorem. Let's start off with C being a positively oriented, piecewise smooth, simple closed plane curve. And let's let D be the region bounded by C. Now let's visualize a vector field over that region as being maybe like the velocity field for some fluid. Now, if you think about this as being some fluid, then you can imagine that there is going to be some fluid flowing into this region, fluid flowing out of this region as well. What if we wanted to sort of consider the net flow of fluid out of this region? So going all the way around the boundary, trying to add up how much flow is going in, how much flow is going out to get the net flow of fluid going out of the region. If we're only concerned with getting the total flow out of the region, then we are only going to be wanting to add up the normal components of F around the boundary. In order to just simply consider the orthogonal component of f, what we'll need to do is establish some sort of normal vector for the curve at any point along the boundary. Probably also going to want this normal vector to be pointing outwards if we're considering flow out of the region as being positive. If n is a normal vector that is always pointing outward, then we can simply get the orthogonal component by taking f dot n. Now remember, when we do f dot n and we are taking the dot product of two vectors, what we are going to get here is a scalar value. That tells us the flow out of that particular point on our curve. And then we have to add up all of the flow at every single one of the points along the curve, and we'll end up essentially just taking the line integral of f dot n ds, since this is a line integral of a scalar function. Now, let's see how we can compute this using Green's theorem and see what we end up with as a result. Let's start off by looking at a parameterization of c. Let's assume that c can be parameterized by r of t, which has the components x of t and y of t. Now, we've seen normal vectors and tangent vectors for parametric curves before. The only difference is this time we're going to actually want to have the normal vector pointing outwards. The unit tangent vector is simply going to be the derivative of r and then made to be a unit length by dividing by the norm of r prime. Now in component form, that would be x prime of t, y prime of t, all over the norm of r prime, which would be x prime of t squared plus y prime of t squared, and then all square rooted. Now how do we get the normal vector from that? It might be useful to draw a little bit of a picture here. And we'll assume that c is going to be positively oriented, and we have a point here on the curve at x, y. Let's start by drawing the unit tangent vector. Our unit tangent vector t hat is going to be just simply tangent to the curve pointing in the direction of travel. And now we want to have our unit normal vector pointing outwards. And we know that these two vectors are going to be perpendicular. So we can always use the idea of slopes in the xy plane to figure out how we can parameterize this unit normal vector. Knowing that the slopes of two perpendicular lines, or orthogonal vectors in this case, must be negative reciprocals of one another, then we can derive a parameterization for the unit normal vector. And try this out for yourself. You can see how in the case where our unit tangent has a positive x and positive y component, our unit normal vector pointing outwards must have to have a positive x component but a negative y component. And that is because we are going around the curve in a counterclockwise direction. Now we have a parameterization of the outwards unit normal vector. And let's see if we can go back and calculate the value of this line integral using Green's theorem. Let's let f be the vector field p, q, where p and q are functions of x and y. And let's evaluate this line integral to get the net flow out. Now remember, when we are doing a line integral of a scalar function like this, we change to parametric form by a small change of variables. ds is equal to ds by dt dt, and since ds by dt is simply just the magnitude of r prime of t, then when we change to parametric form, our ds will be replaced with the norm of r prime of t dt. So let's write this in parametric form. We will plug our parameterization into our vector field. We will dot product with our brand new outwards unit normal vector and change our variable to t. Well, this is very convenient because now you can see that those two norms cancel each other out. Now, to this point in time in the next line here, it might be useful to actually change y prime and negative x prime to Leibniz notation, dy by dt, comma, negative dx by dt. Now you can see that we have dy by dt and negative dx by dt, and our integral is dt. Well, if we wanted to split this up into our component form of the line integral, then this becomes p dy minus q dx, where p and q are functions of x and y. Now it's a little bit backwards. Usually we have our dx first and our dy second. So I'll write this as negative q dx plus p dy. Now it's at this point in time that we can apply Green's theorem. Now with Green's theorem, It may look a little backwards, but we are always going to be taking the y component and looking at its derivative with respect to x, and subtracting the x component and looking at its partial derivative with respect to y. So this becomes a double integral of the partial derivative of p with respect to x minus the partial derivative of negative q with respect to y. And those two negative signs cancel each other out. And that means that we are left with the double integral of partial p with respect to x plus partial q with respect to y. Okay, that doesn't seem like much of a result unless you happen to remember that this is exactly equal to the vector differential operator, or nabla, dot f, which is the divergence of that vector field. As a result, if we are looking for the total flow out of this region, our line integral f dot unit normal vector is equivalent to adding up all of the divergence of our vector field over the entire region. So once again, we have kind of an interesting result. Looking at the net flow out of our region, we really think about probably initially looking at the boundary and thinking about how much flow is going out of our boundary. But in reality, with Green's theorem, we could actually sum up the divergence at every point on the interior of that region. And this result can then also be expanded to surfaces in 3 dimensions. With a surface, we can have an outward pointing normal, a normal vector to the surface, and we may want to consider the flow through that surface, or what we would really refer to as being the flux through that surface. And as a result, this can be expanded to what we call Gauss's divergence theorem in R3. So both of these results are useful on their own, but they are great previews of how we take Green's theorem and we expand it into a further dimension. And the idea that you can be taking a look at the boundary, this line integral, and interpret that as being a sum of some property of the vector field of the interior is still a little bit perplexing at some points in time. How do you find this circulation around the edge by adding up all of the curl from the interior? Or how do you figure out the flow through the edge of this region by adding up the divergence of everything on the interior? It is kind of an interesting way to relate a boundary to an interior interpretation of the same problem. Well, we'll see that again in the future. Thanks for watching, and I'll see you in the next video.